Okay, everyone, thanks for coming to the lecture 7 on the composite beams and the behavior of our columns. So, of course, this part is very important. Basically, there's two type of questions in this lecture, especially for master students. Okay, and of course, this one is very important and very powerful, and of real problems in the industry. Okay, of course, in this lecture, we will deliver or understand the stress in members made of composite beams. Okay, composite, so caused from bending, so other things. That's all the thing. Okay, so because from so far we're only on a single materials. You can understand we have a single homogeneous material will do everything. But actually, in the real applications, not materials always from a single material. For example, even for this disk, there's a lot of different materials. Okay, and so for this kind of case, all the way we learn from previous cannot simply just apply the equation because all the conditions are from a single material. So for these things, we should understand the composite beams, and that's the real things for engineering. So of course, that's why for this lecture we'll understand the following things. So study the stresses in composite beam under bending for this lecture. But the other thing, we have so many things. We understand about joining, torsion, bending, there's so many different things, okay? So that's why for this thing, we're just so far for understanding it because we continue last lecture. And then determine the transformation factor for different materials. Of course, we should transform a composite beam into a homogeneous single materials, okay, beam. Or just say for homogeneous material consists of a single material. Okay, that's what we learned from previously. Of course, understanding the behavior of our columns subject to axial loading and the design of a realistic column against the buckling. So after this lecture, students should be able to determine fracture stress in composite beams and understand the behavior of columns and the concept of critical loads and the buckling. So determine the axial load needed to buck a so-called ideal column. So of course this question, so we're not that hard, but you just know the basic thing, okay? And determine the critical load of the column with various end conditions. Because in the real applications, there are so many different kind of conditions, but I can see some simple way, okay, to do the work. Okay, first on the first part for the composite beams. So in the previous lectures, as I mentioned, we have learned a lot of single material beam. So of course, there's homogeneous, elastic behavior of these things. However, there exist many applications where beams composed of multiple materials. For example, of this. Because this structure, you can see the beams on the top and the bottom are made of steel plates. But inside or between these things is from wood. This is very typical. If you can recall in the last lecture, so all the bend, so normal stress because of a bend from 0 to the neutral axis and to the outer surface with maximum. This means in between the most part, this seems no use, okay, because they can sustain very limited stress from the outside. So that's why this R-beam will be widely used in industry. So that's why based on these things, so that's why for this thing, we still can say we can use these two parts on the top and the bottom parts. This we can sustain the most bending. But in between, that's material mostly just connect these things. So that's why from these things, we should know this from different materials. That's why I say composite beams are made of different materials in order to efficiently carry a load. This is from last lecture, okay? So beams consist of two or more materials, of course from different materials, are referred to composite beams. For example, as I mentioned, this is a sandwich beam. So this is something similar to the previous I-beam, okay? But I-beam, remember, so we tried ideal I-beam for that one, for the fridge and the web, but it must some material connect. So that's why for wood, it's very common for this situation. So of course, based on these things, we can still remember or recall from last lecture, we know the friction formula. So sigma is equal to negative my over I. So remember, there's a requirement. This is only for the homogeneous material and only for single material, because this kind of material based on one structure. So that means this one cannot be applied to directly determine the normal stress in a composite beam. But in real applications, there are so many applications are from composite beam. But how can solve this problem? That means we must use the one way to transfer. So we would transfer into steel, like I-beam. Okay? So that means the cross sections on the composite beam must be transformed into a single material if this formula is to be used to calculate the bending stress. Look on the keywords here. I highlight some. That's the cross section of the composite beam must be transformed into a single material. Why not hard? Because this one sigma is equal to negative my over r. If for torsion, everything based on the location in the y-axis. You can recall, yeah? So that's why for this kind of situation, we cannot change the loading conditions. So that means in the y direction, we cannot change. We only can change the cross-section area. So that's why for here, we will keep the same height, but we will change the cross-section area. So that's because of the equation. Everyone clear? That means when we try to do this problem, we must understand why this thing happened. So I will not ask you to derive the equations, but I will tell you how this comes from. Okay? From previous experience. So every year, there are such kind of questions in the final exam. But many students get 0 mark here. But actually, let's say it's the most simple, I'll say most simple, okay, question in the exam, because there's only one equation to do and it can solve the problems. That's it. But many students get 0 mark. Why? I say, only change the cross section, not change the height. Okay? So of course, how we can understand these things? We just do this thing first. Consider a straight prismatic beam, for example here, made of two homogeneous material. One with a higher stiffness, we'll just say stiff material 1, and then another one with a low stiffness. Let's say less stiff material 2. Everyone clear? On the pure bending. Of course, these are two materials. Then we cannot apply the equation from previously. So that means for this kind of case, we must understand, we must transfer the cross section to use the equation as we learned before. So that's why from here, for materials 1, so they have a elastic modulus E1, and the modulus 2, and from material 2 as a modulus E2. So that's what from here we can understand. But how can do these things? We will try to understand, we will use the one material to transfer to another material, just for calculations. So that's why for this kind of case, we must know how we can transfer them. So of course, these things we say we transfer the cross section. Cross section that means from homogeneous height, and anything we just change the width of these things. So of course, we can do the way. The aim is to obtain a transformed homogeneous beam. That means the material 1 or material 2 transform to one another. So of course, we're through transformation factor. We just say n is equal to n1 over a2. For this kind of case, it's greater than 1, because Young's modulus 1 is higher than Young's modulus 2. Let's say stiff material and less stiff material. Everyone clear? So just know where it comes from. That's enough. Okay. So now, of course, based on this one, we know E1 over E2 is greater than 1. So that N is a ratio of a modular. So that means the E1 over E2 or E2 over E1, depends on the situation. Okay? So of the different materials that make up the beam. So of course, N is used to convert the width of the cross section of the composite beam into a beam made of a single material. That means this kind of thing we can keep the same height. And of course, this equation will not change the load situation because My over R, the Y only in the location of the relative to the neutral axis. So that's what from here, so we can understand this thing will not change the loading conditions, but just change the width. This not change anything because the equation for negative My over R, so only change the Y. Okay? For here, the Y cannot change, or only change the cross section, but this one not inside. Okay? So that's what from this way, how we can understand these things? Remember, we must keep everything in the same situation. And of course, this is linear. Linear, so of course, as we mentioned from last lecture, so this one from neutral axis will be 0. That was a linear to all the surface. So for example, from 0 to some maximum. From 0 to another maximum. One is in compression, another side on compression. Okay, tension, compression. Okay, depends on the situation. So that's why from here, the normal strain will keep the same for the material, same way. So we are vary linearly from 0 at the neutral axis to a maximum far distance from the neutral axis. That's from the beginning where it come from. But remember this time, because of two types of material. We know the strain will change, but then of course, that's because they material will still with elastic deformation. That means, as we know from lecture 1, the Hooke's law will be applied. Sigma is equal to Young's modulus times strain. So that's why from this way, we can work out the normal stress. So that means sigma is equal to E epsilon. But of course, there are two different materials. So sigma 1 will be E1 times epsilon. Sigma 2 will be E2 epsilon for two different materials. So that's why from here, we can get this idea. So if we want to transfer the material, so that means sigma 1, if we want to transfer material 1 into material 2, so that means that sigma 1 should be equal to N sigma 2. But remember, this one, the material, not always in the boundary of the two conjunction of the material. So that's why this one will be changed somewhere. So that's why this one could be from the neutral axis, somewhere will change. That means here, the stress, the normal stress will not always from 0 to uttermost because of the composite. They change the neutral axis. Okay, so far, we just get the idea, okay? Don't worry too much. I will not ask you to derive the equation. But then, of course, how we can get these things done? So, of course, we can see from here. So, you will know force will be equal to sigma times area. So, that means from here, we can see sigma 1 dz dy for this thing, this area of here, for any direction. So of course, that means sigma 1 is equal to N sigma 2. So that means N sigma 2 dA. So this means sigma 2 times N, we can put it inside because it's constant. So that's N dA. So that means sigma 2 is equal to N dz y because we must keep y. Clear? Because y will be related to the normal stress. Because sigma is equal to negative M y over r. So that means we only can change the width of this. So that means the area, so the width will be changed just by times of n of these things. Okay, don't worry too much. So I will let you know how to understand this thing later on, okay? That means use these things to transform a material, a composite being, into a single material being. That means the height h of the being remains the same. This must keep the same. Why? Because we cannot change the loading conditions. Okay? So that's why the h, so the height cannot change. So the strain distribution must be same. So we transform area dA, the width dz is changed, but the height remains unchanged. That means we only change the width of these things. So since we need an equivalent force dF, so which the same magnitude and produce the same moment about the neutral axis. So because we cannot change the loading situation, so that's why we must keep the y as a constant. So without change, only change the width of these things. Of course, the location of the neutral axis of the section before and after transformation should not change. Yes, God, how I can do this? So many conditions. Do not worry, it's so easy. If you understand the concept, even school level, you can do very easily. Okay, that's why you should know where it's come from. That's it. I will not ask you to derive all the equation. Just where it's come from. That's it. Okay. So then, of course, we base on these things. Now, what's the transformation factor? I never heard this before. Don't worry. Just tell you where it come from. The stress in the transform being. Let's say we transformed. For example, as we said, for example here, this one is one steel, one wood. We transfer the wood into steel. But remember, the steel between is not real, it's from wood. Everyone clear? So that's why from here, this is transformed. This part transformed. These two are original. This one is not real. It's from transformed parts. Okay? So from this way, we must get the idea the stress in a transformed being, we say sigma prime, is equivalent to the stress in the same material of the actual being because we cannot change the load condition. So that means before transform, after transformed, the value, the loading condition will keep exactly the same. Otherwise, no meaning to do any work. Clear? So that's why from here, the stress in the full transformed material sigma prime has to be multiplied by the transformation factor n or n prime, we'll do later on, because the area of the transformed material dA prime equal to n dz dy, as we mentioned from here. So that means from here, we will keep the same. That means dA will keep the same. But you cannot see this change because it's not real. One real, one not real. But you must do the work because the area actual times this n. Okay? So from here, we can see dF is equal to sigma dA will equal to sigma prime dA prime because the load will keep the same amount, same direction. Okay? So that's why sigma dA, that's from the real material. Sigma prime dA prime, that's from transformed. That means after transformation. So that means from here, sigma dz dy will equal to sigma prime. This is from the transformed parts, equal to n dz dy. So that means sigma will equal to n sigma prime. So that means after we transform, we work out the equation sigma prime based on the equation, this one, because for a single material. So then afterwards, we should times n to become the real situation. Remember, sigma prime is transformed, it's not real. Okay? It's not the real parts, but it's a transformed, just for calculation. But afterwards, we time n, that's become the real parts. Okay? So that's why from here, to obtain the stress in any transformed material of the actual being. So it must be multiplied by the transformation factor. Once the stress in a transformed material is determined from the fracture equation. Sigma is equal to negative my over r. So, I said, sometimes we use m prime will be E2 over E1 is less than 1. And of course, this is the most widely used situation because we want safe material. Remember, if m prime is equal to E2 over E1 is less than 1, then of course, n dz, that means cross-section will become smaller. That's why save room, save material. Okay, so I said it's the most used for saving material because a smaller sectors is transformed when a section made of the material with a lower stiffness is transformed into that with a higher stiffness. So I highly recommend you guys use this way. Clear? That's way more easy because it's save material. Otherwise, you will draw so long or so wide. There's no room for you to draw for this. So now, I will tell you how I can do this problem. Okay, this is very important. That's why I highlight here on the top. So this one also highlight, but we'll tell you where it come from. Okay, we'll understand where it come from. But that's the way. So it's the real way how we can do the problem. So when we transform, I try to put many things here. We can transform the beam to an equivalent beam made of materials one only. For example, here 1 or 2. So for the one with a higher stiffness, that means your smaller one is greater than the material with a less stiff material 2. So if we want to transform the material for 2 transform into 1, so that means the structure only with the material 1. Everyone clear? Everyone clear? Okay, for this kind of case, so we must convert. This thing is very important for you to work out, okay? So that means we can draw like this way. This material 1 will keep the same, and the material 2 definitely will become smaller because, as we mentioned before, this one will based on this, n dz. So that means that E2 over E1 should be less than 1. But how can you know which one is E1 over E2 or E2 over E1? Easy. I'll tell you how. Everyone look carefully. Look at the slide. I highlight some parts. Last parts. Okay, n or n plus doesn't matter. N if equal to E2 over E1 on the top, that's the material to be transformed. Or say from this material to this material. From 2 to 1. Everyone clear? So the bottom one is to be transformed or transformed. That's after transformed. So that means from 1 or 2. Block here, from 2 to 1. So the material to be transformed will be on the top. And after transform in the bottom. Everyone clear? So that's why from here I highlight AC. From 2 to 1. So the A is equal to E2 over E1. Because E1 is greater than E2, so that means here less than 1. But after transformation, and look on the screen, everyone. So of course, we should solve the key thing is find the width after transformation. So that means that B1 is equal to NB. B is from original one. After transformation is B1. So B1 is equal to NB. So N is less than 1. So that means here should be smaller. Everyone clear? Okay. That's the key thing. Okay. Otherwise you put wrong things. So then of course based on this thing, this is from single material, that's very easy because that's from this kind of T shape. Easy. We can work on the neutral axis easily. We can work on the fracture equation very easily because sigma is equal to negative my over r. Done. Easy. So that's why from here, we can work these things. Just use a single material. That's what we did as in last lecture and tutorial. So clear? Okay. So of course, based on this one, After we get these things, remember, this is transformed parts. This is the real case. So that's why for the after calculation, we can use this equation to work out. Calculate the stress in the transformed material Y is a sigma prime. So the number you calculate is sigma prime. It's not real one. Okay, just replace this thing. That means transformed part. Sigma prime and the stress in the transformed material of the actual beam. So for actual beam is from here, not here. It's here. So it's less from 2. Then we can multiply the n. So that's E sigma 2 is equal to n sigma prime. So that's why E2 over E1 times sigma prime. Clear? Sigma prime is from the equation we did based on the equation. Okay? So that's why from here, we can work this easily. So that's why from this way, we can work out. Okay, we can also have other case. Because two material, I can also transfer from material 1 to material 2. That means from high stiff material to less stiff material. For example, here. So stiff 1, less stiff 2. So of course, only with the material 2, that means we transform material 1 into material 2. Clear? So of course, you see N is equal to E1. On the top is a material to be transformed. E2, the material after transformation. So that means we will transform material from 1 to 2. Everyone clear? From top to bottom. So from here, we can get greater than 1. So after transformation, the D2 will equal to NB. Of course, N is greater than 1. Of course, the width will become larger. Everyone clear? This is namely key, okay, when you try to use these things. You should know which material is transformed, which materials are the transformation, okay, from the equation. N is equal to E1 or E2, depends which material will be transformed, okay. From this one, on the top, material to transformed. The bottom one is material after transform. Okay, so the one I use color to show you. You can see for the material 2, this is A2, the bottom. For material only after to 1, the bottom one is E1. Okay, that's why this is very important for you to know. Okay, so of course, based on this one, easy. Then afterwards, there's a material all from wood, for example, from this material. This is also T-shape. But this one also single material, we still can use the problem, the equation from the sigma equal to negative my over r. We can work out, but we must time the n. So sigma y is equal to n times sigma prime. Remember, sigma prime is worked out from the equation in the material after transformation. Clear? This is not real material. It's not the actual material. It's from the transformed material. So that's why we use prime to mention these things. Okay, we can show you an example to show you how this thing will happen. Okay, a composite beam is made of wood and is reinforced with a steel strip located on its bottom side. Its cross-section area is shown here on all the things, the numbers. Okay, if the beam is subject to a bending moment, this bending moment here, that means here on the top of the neutral axis will become bending in compression. On the bottom will be in tension. Okay, so of course we know determine the normal stress at the point B and the point C. Take the Young's modulus of wood is 12 gigapascal, and the Young's modulus of steel is 200 gigapascal. If this is only single material, that's from previous. Clear? From lecture 6 and tutorial 6. Everyone clear? It's from single material. We work on the B and the C, easy. We did several examples for lecture and tutorial questions. So, but this time it's a two type of materials. Then the equation from sigma equal to negative ny over r is not valid because there's two materials. So that's a composite beam. So that means to be valid, then we must transform the materials into single material. So then we can see here how can we make this thing. As I said, we try to save room. Of course, we can use which one is less, which one less material. Wood, 12 kilopascal. Steel, 200 kilopascal. That means we should transform wood into steel to save material. Clear? So of course, wood to steel. So that means A is equal to E wood over E steel. Clear? From materials 1 to materials 2. From materials 2 to materials 1. Okay? That's why from here, we can transform here, the transformation factor. A is equal to wood to steel. 12 to 200 is a 0.06. That means we will transfer the whole thing from wood to steel. That means in the end, this material will only with steel. So single material. So that means we need to work on the width of the transformed parts. This 150 times N. So N B steel. So remember here, B wood prime after transformation. So equal to N B steel. So equal to 0.06 times 150. So that means only 9 millimeter is here, 9 millimeters here width. So that means only one with a T beam over here. So that's why here we can work out this easy because this one all from previous law. So that's why from here we can work on the neutral axis. Y is equal to summation Y bar A over summation of the whole area. Of course, it's quite a simple way. Y is a rectangular one, Y is a rectangular one. So I'll put a text here, highlight. For bottom one, the halfway will be half height. So 0.02 divided by 2 central times the area plus this one half of 150, but still plus 20. Okay, that's why here 1.15 over 2 plus 0.02. The area same. That's why we can get this thing with 0.03638 meters of this thing from bottom. Everyone clear? So this from lecture 6 and tutorial 6. And later on, we can work on the neutral axis and we can work on the I. Okay, moment of the neutral axis. So this one, remember, you must know how can use a parallel axis theorem. So I will not repeat all the things, otherwise we cannot do any work. So that's why I can see, I put a text here, highlight here, you can see from this thing. That's the reason we must get the neutral axis related to the neutral axis. Okay, centered over each rectangular relative to the neutral axis. That's why here is the distance. Here's distance. You can work out. Okay, so this from lecture 6, tutorial 6, and also these things from exynology in the lecture 2, tutorial 2. So obviously a single material. Now of course we can work on because there's a B is here in the wood, but unless we transform, we become B prime. Remember, the put prime that means not real material. Okay, it's from transformed parts. So that means we can apply this equation in the B prime and the C. That's why we see here. Sigma B prime is equal to negative my over r because only single material. So that's why from here we can work out. Remember, we must know the distance. Okay, so point bottom 0.17. So because of 0.15 plus 0.02 minus the neutral axis. That's why you can get these things. You see negative 28.56 megapascal. But remember, this is sigma B prime, not actual. Clear? So then, of course, sigma C is about real material. That means with negative my over r. we can see, remember, this is below neutral isolation. That's what's selective. So that's why here we can say 7.78 megapascal. So far, these two are the same as lecture 6 and the tutorial 6. Clear? But remember, the B point here, B prime is not real because this one is from steel. So of course, the real one, actual one is from wood. That means we should use a sigma B is equal to N B prime. So N is 0.06 times negative 28.56. That means 1.71 megapascal. So that's why the sigma B is this value. Everyone clear? Why I mention these things is very important for the N, because you put it the wrong way, your answer will be totally different. Because many students, this is where's the N? I said you must know where it's come from. Okay? So that's why from here, we only took one more step, just because we must transform the composite beam into a single material. And the other thing quite easy, because that's from lecture 6 to 26. Okay? So of course, it's quite a similar way for this thing. That's why for one, there's one question in the final exam in the pre, but so far I don't know, okay, because I still not start to design the final exam question, okay. But after mid-sem exam, I would start to design, okay. So that's why for these things, for last few years, we must have such kind of question, similar way, okay. But you must transform this structure. Okay, we see another question for this. So reinforced concrete beam has a cross-sectional area as shown here. So if it is subject to a bending moment of 60 kilonewton meter, determine the normal stress in the steel reinforcing rods and the maximum normal stress in the concrete. So take the Young's model of a steel, 200 gigapascal. The concrete Young's modulus is a 25 gigapascal. That structure. This is very common in civil engineering because this steel bar reinforced concrete. Because the concrete only can sustain the compression, but you must put some steel bar inside. For every tall building, there must a steel bar inside. Okay, if you can observe some construction on site, so always steel bars in the concrete because they can sustain the extension or some other thing, or torsion something, okay? But concrete, pure concrete, only can sustain compression, okay? So this is very common, but remember what the steel bar, but the other thing is rectangular. Remember, as we mentioned, we must keep same as an area. Because the steel bar is a circle, so that's why we must consider for the area. So remember, we try to save the material, so that's why we say from low or less stiff material to the high stiff material. But this time, because the steel bar is quite small, and the concrete is quite big. So if we transform the concrete into steel bar, that's even smaller. It's very hard to work out. That's why for this time, we can convert steel bar into concrete. So that means we can use a transform steel into concrete, become bigger. Because otherwise, it's no way to draw the figures. Everyone clear? So that's why from here, we can take transformation factor from steel to concrete. Transform, which one will be up? So that is the question. This one follow me. You can say, oh, that's because from steel to concrete. But when you do the question by yourself in exams, you should know which one is which one. Okay, in the tutorial, we will do together. Okay, so to find where's wrong, where's correct. Okay, so but just let you know, we will transform steel into concrete. So it's about 200 gigapascal to 25 gigapascal, which is 8. So of course, as a steel, so the width this will times n. So because steel bar quite small, we'll make a big one. So that's why we can n times b concrete of this thing. So then we can remember, because this time it's a one circle, one is rectangular one. We must remember, we must consider the area of the one. So that's why we can see from the beginning, this is from area. It's n sigma 2 dA. Sigma 2 n dA, that's what to come to A. So that's why from here, we can go like this way. Concrete, steel bar, we can use concrete as a rectangular one. So, but remove this part because this part cannot sustain tension. So that's why there's no meaning to put these things for concrete under the neutral axis. Everyone clear? So that's why from here we can get these things. So that's why from here we can go to the area, the steel with 2 times because of 2 steel bar. So pi r square. So we can get it. So now of course A prime will be N A steel. So that's about 2 times pi times this the square. So what we can get is the area. But because this one's very, very small. Okay? So from here, we can still do anything here. Let's put text here to let you know. Note that concrete cracks in tension. So that's why there's no meaning to put anything under the neutral axis. Okay? So that's why from compression in section above, we can put it. But below, there's nothing. Okay? Because this one can only in compression, cannot sustain any tension. So that means for here, we can see the area of concrete below neutral axis is not included for calculation because concrete cracks in tension. There's no meaning of this thing. This one only replaced by steel bar. Okay? So of course, we must work out anything in the Q. So we find out where's the neutral axis. Neutral axis from lecture 2. This is from the first moment area. The first moment area above neutral axis will be equal to 0. Okay? And then, of course, we can put all the things together. Because on the neutral axis, there's no any moment. So from here, we can work on this area, 0.3 times h prime, even though they're upwards. And the minus, because it's below. So this one will equal to 0. So now of the equation, we can get on the h prime will be 12.09 meters. So remember, this all from the original meaning with neutral axis. You can go back for engineering mechanics, you can see. So all the neutral axis, that means this one will be equal to 0 of these things. The first moment of area at the neutral axis will be 0. This is from definition. Okay? So then later on, we can work on this R beam. We still consider one way. Consider the parallel axis theorem. But look here, we work on the bottom one. Here's 0. Why 0? Because this is a small one. This means this is very, very tiny of this. That's why we can ignore this Rx for this one because we say it's 1 point. But we can put the area of these things. But because R is here, so we'll put only with these parts. So then later on, we can work on the whole thing. So we can work on the sigma concrete max on the top. So that's why we put negative my over R above. That's why we can see this value. So negative 9.20 megapascal. So this is compression. Remember, this is real. It's actual concrete. Then later on, we can work on the normal stress, okay, under the bottom one, because it's from the transformed concrete. It's not real. It's transformed concrete. That's why I say sigma prime concrete. So that's mean concrete after transformation. So negative my over R, we still can work out is 21.24 megapascal. But remember in tension. But remember, we must convert into sigma steel is equal to N times sigma prime concrete. N is a transformation factor. This one after we from the calculation from the equation. So that's why from here, 200 gigapascal over 25, we mentioned before, times 21.1 is 170 megapascal. So that's why from here, we have a much higher stress in tension. That's why we must steel bar. That's why for we put many tall buildings, you will see the size of the steel bar are a lot of different. When building tall, the steel bars are bigger. If just smaller one, they just have the smaller parts. So that's because they can put a lot of large tension inside. Okay, that's why there's one there. Okay, last parts for this first part. So of course, this one is a little bit hard to understand, but these things you must know. For the example 1, You must understand. That's why in example 1, I highlight in yellow. Clear? So this part you must understand. Okay, we will have a 10 minutes break, then we'll come back. Okay, we'll continue the second part. Second part on the buckling of our columns. So in the previous lecture, so especially we start from any lecture before. So we know the strength of a material. So are considered for calculations. It's better for yield strength. So if you can remember for other design or anything for the structure. So the yield strength is one of the key design parameters for this. But however, in many cases, the yield strength is not always the one way to do. Okay? Especially when some special situations. For example, for columns. Okay? This one, for many columns, we need to consider for the safety of the requirement. For example, for the stability. Okay, so of course the just strength is not enough or insufficient for design. If you still can recall for the torsion, we understand there's one moment torque and also have one angle of twist. We should design one of the parts based on the design criterion. But for beams or columns, so you will only consider the yield strength, or even we consider the safety factor, it's not enough. Many of you have conducted the lab sessions in the column behaviors. You can remember for the so far it's group 1, 2, 3. So they did it. Next week we will swap. Okay, this week we swap. But those is for the that's a buckling of these things. So see they stabilize. For example, when we show anything here, we put a beam, they put this one as a low load. But remember one thing, they were not just broken, they were bent for these things. That means it's not stable. It's not. If they bend too much, this one that means no use already. This is also fair. So from here, so we should consider one way. So stability is better for structure. Stability is one of the very important design. So that's why for here, we should consider the stability. So I'll put a comment here. Structural members are required to be stable in addition to satisfying the relevant strength and the deflection requirement. So that means stability requirement must be satisfied. For example, you want to see one chair, and that chair is not stable, we cannot use. Okay, so of course, it's so important for this thing. Stability is particularly important if the structural member is long and slender. Okay, and the compressive load is high enough to cause the member to suddenly deflect laterally or sideways, like this way. Even it's load, but it's a bend like this way. So this one will be no use. Okay, so even this one not break, but still fair because not straight anymore. Okay, that's all for this kind of case. We should understand what means called column. Column is a long, slender member subject to an axial compressive force. Remember, only in compression, not in tension. Okay, so and of course are called columns. Buckling, so that means the lateral. You can see here. This will cause member to suddenly deflect laterally or sideways. This means the lateral deflection that occurs is called buckling. So that's for this thing. It's buckling happened. So buckling is one of very important failure. It's better for slender columns. Okay. So of course, this one buckling may lead to sudden and dramatic failure. So this means not straight enough. Okay, so of course you put it here, you put a band This one already, because of the structure hold, structure not stable, not stable. So that's why for here, you must consider here it's a straightaway or bend. The structure stability is one very important thing. So for here, so we should consider buckling. But remember for the buckling, we should consider here the buckling. When we put ending here is a load put. We come to some critical value. That's buckling will happen. So that means the maximum axial load that a column can support when it's on the verge of a buckling is called critical load, PCR. So critical load. So that's here. Put one load and then set away. So that is a maximum value you can put. You put less, no change. Less, no change. Put a little bit more, and start to change. So that's on the boundary. That's called critical load. This load also called Euler load because with a Euler function. Later on, don't worry, where your words come from. So that means the buckling is one of the very important failure mode for slender columns of these things. Even this load is far below yield strength. Okay? But how we can understand this way? So that's why first thing, we should understand how the buckling will happen. That's why from here we can understand the idealized structure for this mode. We consider the below the two bar mechanism consists of the whether it is rigid bars, one here, one here, but are pinned and also connected somewhere. So if we put one spring, then of course spring were stretched. Compression could be stretched, could be compression. So of course based on this one will move. If this one is stretched, this one will come to this side. If compression will come to this side. Doesn't matter which side they go, this one will result one force because spring, where if you can remember, the force is equal to K times the change of the distance. So we learn this one from lecture 4, I think. So that's why from here, we can get a load for the rigid bars of these things. Of course, if this one from equilibrium condition, we can work on this load. This one load, this one load, this one nothing from the usual no loading condition of this thing. But any small disturbance of A, either in stretch or in compression condition. For example, here in compression. Of course, in compression, of course, this one put one load. You can remember, yeah? We mentioned this before in the axial loading. So the one from here is one loaded, but this one must put in equilibrium. That means you want to draw free body diagram. This load and then this load will be equal to this load in sum. Put a summation of a fx equal to 0. So summation of 1, this one, of course, these two parts will be equal. But fx, because there's a spring here. So as well from here, we can draw free body diagram. Okay, so of course, you can see here is one load along this way because of stretch. And now, of course, the load went this way. Of course, we can get free body diagram. The old fx will be summing fx equal to 0. So that means here the free body 2p tangent theta will be equal to f. F is equal to k delta. Okay, of course, that's why from here we can work out. But this is because of small angle, just a small disturbance. So of course, delta here will be equally to the, remember, there's a theta, there's a L theta will be the arc length. So that means here will be equal to delta is equal to theta times half L. But remember, this theta is small, so of course tangent theta will roughly equal to theta. This is from school math. So that means we can put here 2p theta is equal to k theta times half L. So we can from here. So theta can be cancelled. It's non-zero, can be cancelled. So that means the p is equal to quarter KL. or KL divided by 4. So this is nothing independent of theta. Doesn't matter how much they move, they will keep their position. Okay? So that means from here, this thing is called Euler function. Okay? But the Euler function a lot of functions. So let's call the Euler load P depends on K and L, independent of theta. So that's why from here, we can draw the fluid body. We can work this equation. Of course, for this situation, we can work out. But actually, we come to the real case. I put a comment here. That's why I put an empty here. P is equal to KL over 4 represent a case of the mechanism being in neutral equilibrium. Of course, because P is independent of theta, as we mentioned from this derivation of this equation. So this is, of course, independent of theta. Any slight disturbance given to the mechanism will not cause it to move further out of the equilibrium. That means go to any location will keep equilibrium condition. Okay? So nor will it be restored to its original position. That means the after release load, they will not go to its original position. That's why for many cases after buckling, this one cannot restore to its original straight position. No, this already failed. Okay? So that's why from here I put the text here to let you understand. But we're keen to know where is the boundary. We want this one put a load, but we restore. Okay? So that's why we should know the situation. For this kind of case, if P is greater than KL over 4, of course, it's unstable equilibrium. So that means we'll go back somewhere. If P is equal, this is a neutral equilibrium. Even let's say we're stable equilibrium of this. But of course, there's some where bifurcation point somewhere is where there's two locations. One is stable, one is unstable of these locations. So of course, put it here, important. Once the column bucked, the column becomes useless and cannot support the loads anymore. So therefore, buckling is a very important phenomenon that we should consider in applications. That's why I put a text here on these slides. Clear? I still highlight on yellow on the top because it's very important for you to know. So buckling is one of the typical failure modes. So don't just say we go to yield strength. Okay, I put a text here to let you know because that's why this can help you understanding. This one nothing for equation, but will help you understanding of these things. So how can get the ideal column? So an ideal column should satisfy the following conditions: perfectly straight before loading. Okay, that's straight column, and made of homogeneous material. You cannot say this one could be some change because the whole thing will be changed. Okay, and behave in a linear elastic formation. That means the Hooke's law can be applied, and the pin supported at the both ends. Pin supports, pin, okay, supports and ends. And of course, load throughout the centroid of the chloride. That means the load should be passed through the neutral axis. But this is very, very strict. If you still can remember, we have learned before, inclined position. That's because not all the load will pass through the centroid. For example, when I push the disk, I should find where's the neutral axis. No, we can push anywhere. Clear? Otherwise, we should find out. We should work out where's the neutral axis and pass through. There's no way to do these things. So that's why for many cases, it's not that case. But this ideal location, so to put these things. But in reality, some of these conditions never satisfy. Okay? Bending over the column, so that means the applied load will not pass through the cross-section center. So maybe somewhere have a small lateral deflection considered for this situation. That's upper text here for you to understand, okay? So for any listed way, as we mentioned in the parts, so for any ideal column, the axillary can theoretically increase until failure, until yielding. Everyone look on the slide. This is so important. I say, you put many tests there, you should know these things. This is one way critical for exam and for calculations. Okay, even I didn't highlight here, but it's the one way as we mentioned before. So when the axial load reaches the critical load, is on the verge of becoming unstable. That means buckling will occur because of PCR. I put the text here, happen. Clear? Unstable. That's a buckling will happen. So that's what I put here. But in one way, slight reduction in P will straight up the column and slightly increase in P will cause further lateral deflection. That's why I put here for on the text in yellow on the top. I just expand here to let you know these things. Everyone clear? So this is very important for you to know these things. So of course, that means we should know the critical buckling equation is so important for us to work out. But how can get this value? We will use an example to show you. Okay, also tutorial to show you how can this happen. But before we do many things here, but remember there's so many things could be happened. Okay? But how can get these values? So we can use an example to show you. For the idea of this thing, we can get anything over here. We can see, hey, this one put one load a little bit, and this one put a load, and get up a bend a little bit. But remember here, as I mentioned, if only the load is greater than its value, so this will become unstable. So that's why for here, only on the load, the critical value, only higher than that value, this will become buckling. But smaller than one, after release, this one will restore to its original position, will straight up. So that's why from here, we must get this idea, how can we put the loads here? Change. So it's from here, we still use this spring to simulate this thing. That's why we can get anything here, but kappa is equal to d theta dx. We learned this one from lecture 4, lecture 5. Everyone clear? But because it's small one, the d theta with kappa is equal to d theta dx. You can go back to lecture 4. So of course, d theta dx will be equal to second derivative of the moment of the displacement and is respect to x. Don't know what, this was letting you know where it's come from, okay? That means we can go further. Kappa is equal to second derivative of displacement v with respect to x. Remember, this is for the linear material. Of course, the sigma material is equal to E epsilon. So this one we'll learn also lecture 4, okay? So sigma max will equal to length mc over r. We can put it all together, we can get this equation. That means we can use math to work out this equation. So of course, the critical mode will be P is equal to n square pi square ER over L square. A will be 1, 2, 3, 4, 5, 6, all the integer values. Because this one could be as here, this way, and the other ways. This one is a 1/2, 2/2, 3/2, 4/2, 5/2. That's so many continue because they will change the shapes. Okay? But remember one way, if you go to 1, that means already buckling happened. So there's no meaning for second or third or something, no more. So even for happen, failed. So that means here, we can get this idea for one mode shape. That's way for workout. But we should know where it's come from. Okay? So that's why from here, we can say P is equal to n square pi square ER over L square. But because already one mode happened, already failed. So that's what we don't care. 2 half, 3 half, 4 half. There's no meaning. So that's what 1 half. That's it. That's already failed. So that's why from here we will use the equation for the P or Pn column. P will be equal to n equal to 1 is P critical is equal to pi square E R minimum over L square. So this is very important for you. I will explain this thing, what's happening for here. So as I say, n equal to 1 because that's from the meaning, yeah? 1 half, second half, third half, fourth half, fifth half, continue. But already failed, 1 done. So that's why I don't care for second, third, that's nothing. So that's why if this one reached, this part already failed. So that's why from here, we can only n equal to 1, we get this value. But remember, this I must be the minimum or least value of all the principal axes. Let's put the text here. Everyone look carefully, okay? This is very, very important for you when do calculations. The PCR corresponds to the minimum moment of inertia of R minima. So that means one of the principal axis. So this one is R minima. For example, if this rectangular is R beam, you will see which one's values is bigger, which one is smaller. I put the text here. Okay? So the cross sections of the column showing the principle of this one. So of course R1 is greater than R2. So you can work out. If R1 were equal to 1 over 12 BH cubic, R2 will be 1 over 12 HB cubic. You can put any value, you can find the value, which one bigger, which smaller. Okay? Same way of this. R1, R2 of this. Which one is R1 and which R2? So this one will bigger than this one, R2. So of course, this one, we should find the minimum value for calculation. Of course, we found here, this is the key thing, after we know from previous text. This key thing is for calculation, and they get a right value in the exams, okay? Why we care about for the critical values? There's two conditions. For most of material we design, we say, hey, this material's the stress is higher than the yield stress. This one design, bang, break. So that means the yield stress is the critical value for design, for most cases. But for small or slender columns, so of course this situation will change. So for example, sigma greater than sigma 1 permanent shape change or value. But even for the load much less than sigma 1, but sigma is greater than the sigma critical sigma. So from PCR divided area. So the critical stress, the corner will fail as a buckling because this one will reach the critical load. So that means the buckling will happen. Even the load is less than sigma 1, will not failure because of the change of the shape, but this will change in the buckling. So that's why this kind of case will also fail, but fail is buckling. Not fail is a permanent plastic deformation. So these two fail models are different. Everyone clear? So of course, based on this one, we need to calculate critical stress for buckling to ensure safety requirement. So that's why for these things, these slides, you must know the meaning of this. So based on this, then of course, we can get these things. PCR is independent of the strength, but varies of material stiffness. Only with this thing. That's why there's nothing with the yield strength. It's only care about the Young's modulus. put a hidden text here. PCR is a pi square ER minimum over L square. Just copy it to here. Okay, I get a full detail understanding. PCR is critical or maximum axial load on column just before it begins to buck. So I put text here, this load must not cause stress in the column to exist the proportion limit. That means you must verify the results. So that's why from here, I put text here. If this load is greater than sigma 1, that means there's no buckling, because before buckling, this material already failed because of the plastic deformation. So that's why for here, you must get at the point. Must not cause stress, so exists the proportion limit. E is a modulus of elasticity of the material. I is the least moment of inertia. So that means if several locations, you should find which should be for the R. For example, for like a tangular one or the R beam, you should know which one will work. That means you should work to R. R1, R2, you should work out by yourself. L, of course, is the end on pin. But the one way, for any design here, so we should know what kind of value we should work out. So basically, we use radius of gyration of these things in terms of this new workout, because we can further input this value, PCR over area, and we'll put every value here, pi square E. They put this R of A inside, and the L square is name. So then we can put the values inside. Of course, we still can work on the sigma CR, so critical stress. So pi square times the E over L over R square. Because this is from slenderness ratio, this is very common for many design. They will say, hey, the slenderness ratio is blah, blah, blah. They will tell you the numbers. That's why this one can put this value very easily. You can work out. Okay, this is from engineering design of these things. But remember, all are the same. Just care about remember highlight parts that requires that sigma CR should be less than sigma Y, and this is very important. So please don't ignore these parts. Okay, in the calculations, you must verify these parts. Otherwise, there's no meaning of your work. Everyone clear? So that's why I highlight again and again. It's so important for you to realize. Other things quite easy. Other things, so R is smallest radius of a gyration. So of a column, this one can be used design, because use the design of a column. If you buy column from market, they will always tell the value of this thing, slenderness ratio. They will put the same value of this thing. You can buy from market based on standard ratio. You can see from market. Okay. Again, realize we need verify whether sigma CR is less than sigma 1. So this is a very important step to avoid buckling of columns. So this is so important for you, okay? Otherwise, the meaning will be totally different. As I mentioned, the failure of the parts will be different because of a different situation. So that's why please realize it's so important for you to realize. Okay? Okay, we got anything here, we can get anything here because this is for engineering chart. So they can get this value, see from the different structures. You see from here, you see the slender ratio of these things from the chart for engineering design. So any design here, of course, we can see from design. If you still can remember, sigma CR should be less than sigma Y. Everyone clear? Look for the here. So this material, for example, we know from the chart, we know the material sigma CR. Look here, sigma CR. So of course we can see sigma Y is 250. Sigma CR for this one still. You see, that means this one, if this sigma CR is greater than sigma Y, this one, what happened? This one below, what's happened? So you should know the meaning. So that's because from here. Okay? So from here, we can check the value because of these things. You see, I put the text here. Then you know how can draw, how can understand the picture. The critical stress curve are hyperbolic. That means the curve. Hyperbolic is for the engineering chart. We get it from many of this. This is for steel. This is for the aluminum. We get the value. So that's why from here, we can get these values from the P end column. So from column of course, L over R is 18.9 from the steel column. And also this one is 6.5 is for aluminum from the chart. So that means for steel is less than 89. Sigma CL will exceed sigma Y before the box. So that means the corner will fail at yield first. So that means there's no buckling. It's fair because of plastic formation. Clear? So that's why we should know how we understand this chart. That's why I put the text for you to understand. So that's why from here, this is from the engineering chart, we get some values. Only less than, that's way be for yield strength. For only for this way, this one will be for buckling. Okay? So that's for this thing, we can get it as an idea. So again, we must do this thing. If sigma CR greater than sigma Y, we need to use the compressive stress equation. Sigma is equal to P over A. So of course, sometimes we need to also consider the safety factor N. Okay? So of course, this is the maximum stress is the yield strength. And of course, sometimes we need to consider safety factor. So let's from lecture 1. So that's why for these two, we should consider the cases. Sigma CR must less than sigma Y. That's for buckling. If sigma Y greater than sigma Y, that means this is for plastic formation. So that's different value model of these things. Of course, based on these things, sometimes there's some other things we will do. So, but of course, there's a situation with you. Not all the thing will be pin on the two ends. Something with the other things happen. So that means from here we can consider for effective length. For example, for this one is fixed in the end, but one is freestanding. Of course, put one note there. But for this kind of case, they still also produce, if load is enough, is also produce buckling. But we see like this way as a one extension, that's about 2L of this thing for effective length for this thing. The effective length is the length of equivalent pin end column. So all the distance between the point of inflection. So for this kind of case, we say this one effective length is equal to 2L. The L is the length of the column, but for this kind of case, something similar to the two pin end parts. So that's why for here, PCR is a pi square ER over LE, so effective length of these things. So of course, this one still we should consider these things. So for different situation, this one could be effective length factor K will be put inside. So if K is equal to 2, so let's say if you can still remember, this will be something as we learned before. If equal to 1 is equal to pin and corner of these things. But this is key thing. It summarizes all the things together. For different situation, this value will be different. I highly recommend you further on that page. If you have a book, you can further that page. If you don't have a textbook, this equation I also provide in the specific question in the formula sheet. Okay, I will because I cannot find this thing. Don't worry, I still provide to you in the solution. Okay, but I highly recommend you to understand for different situation, you must know what the number will be. So there's nothing to explain, just summarize all the things together. Okay? But remember one thing, I still put a text here. The Euro-Buckling theory used is valid only if the column is perfectly straight before the load is applied. So that means we need to consider this is a linear elastic behavior and also only have a small deflection. Otherwise, there's no meaning of the values. So we use example to show you how we can understand these things. Okay? Here the question is quite long. Yeah? This is a situation. So this is very common. I think it's better in Australia. It's very common for these things. Okay? It's called outlook. So very common, especially just close to ocean or called beach. There's a lot of such kind of outlook of these things. So this view platform is in a weird animal park, as I show here. It's supported by a row of aluminum pipe. So corner have a length of 3.25 cm length here, and all the diameter. So this will tell you that's a tube, so 100 millimeter. The bases of the column are set in concrete footing, and the top of the column are supported laterally by a platform. That means they can shake. Okay. So the column are being designed to support compressive load. P is equal to 100 kilonewton. So determine the minimum required thickness T of the column. In the factor safety, safety is n equal to 3 because the safety factor, okay, is required with respect to the Euro-Buckling. For the aluminium, we use the Young's modulus of aluminium is 72 gigapascals, and use the proportion limit sigma y is 480 megapascals. Of course, based on the situation, we know one is fixed and one is the pin. So that's why from here, one fixed, one pin. Clear? As a situation. So that's why we will use the equation to work out. So that's why from here, we can get this equation. Copy to here. So of course, that's what we can see from this knowledge. You see the base of the column is fixed by concrete. That's be fixed. And the top is supported by lateral platform, that's a pin, like this way. So that's why we can use this equation. PCR is this equation. Clear? This one here. But then later on, we can work out the equation. It's R for a tube, and also for the required thickness, PCR. Remember, this is a safety factor. That's what we should consider for much higher of this thing. PCR should be NP of this thing. So 300 kilonewton will support for design. So then, of course, we can put the values here. Put all the things, this value over here. So then, we can put the values here by use equation for the math. We can work on the T is 6.83 millimeter. We can get these things. But remember, we work here, it's not stop, not finish, it's here. Because we must modify, this one is for buckling. Remember, it's for buckling. For buckling, we must work on the PCR or sigma CR should be less than EF strength. I mentioned all the time all these things. You must modify. So if just work here, we assume this one will happen, buckling. But when you work here, that's for buckling. But whether it's for buckling or not buckling, you must modify. If not for buckling, all your calculation is not suitable. So that's why we must modify the calculation. So you must do this step. Okay? So of course we can get a moment of these things, we must get a generation of these things, but don't worry, this is that you know these things. Okay? But the key thing is here, sigma CR is a PCR over A. That means you work on the A, that's 150 megapascal. Clear? So this one is less than 480. So that means these things will happen. So that means when this work out, the sigma CR 150 megapascal, this one is less than 480 megapascal. That means the calculation for the critical loads using Euro-Buckley theory is satisfied. So it's a valid value. Clear? So that's why this is very important for you to understand. We must modify the value, whether this y is less than sigma y or not. If less than sigma y, that means it's valid. If higher than sigma y, that means the value will be sigma y. That means from here. Okay, and then we do here calculations. So from here, we must do these things. If sigma CR is greater than sigma y, that means the value should be used sigma y to replace sigma CR. Okay, that's for design. Okay, that's why this is very, very important for you to understand. So this part, you cannot ignore this part. Okay, of course, based on these things, we can do this kind of work. But how we can get this thing done? So that's basically your understanding of the results. Okay, so we still have a short tutorial, short question over here. This is quite simple for the calculation. Okay, so this was still with the member will tell you the width and the thickness of the member shown in the figures in the pin column. So the parameter of the member is to tell you the area Rx and Y. Rx and Y. Okay, will tell you. So it means that you don't need to work out. Okay. Determine the largest axis load it can support before it either begins to buckling or steer ears. That means could it be buckling, could it be yielding? Okay. So that means from here, we must find from the equation. So remember the equation tell you I should be minimum value. Clear? So that means from here, we get the value R minimum value. So because the Ry is less than Rx, clear? So that means this one will get this value down from here, Rx first. So of course we can get a PCR is from here is a pi EI over L square because only mentioned to you is a pin connect column. So that's the equation will be here. We can work out this value. Sigma CR is PCR over A. We can work out easily. So then of course we can find this higher or less than sigma Y. This one 570 megapascal higher than 345 yield strength. So that means the sigma should be used sigma Y to replace. So the P is this value. Clear? So because we are first yield, buckling will not happen. So of course, this is one way. Same way we can do this way, we can still do it one way, we can work out. Still give you still bar for the different situation and also fix it its end. So that's what end. But we put end fix. But we still, you put load, we still buckling or yield. In the loads on the YY direction here. And also the pin connect to each midpoint, the pin here. So that's why we should know where's the situation. Tell the A, tell the Rx, Ry. That's mean you don't need to work on any of this. Determine the load it can support so that the column does not buck or the material exceed the yield strength. That's what we should find. This cannot yield or cannot buckling over here. We'll tell the material structure, material property. So of course, based on this one, we should know where's the structure will be here. So I put here the slide 23. I put it here, let you know as from this structure. Okay, so which one you should select? Pin, or fixed. Okay, this one you should find by yourself. So of course I put the text here, so that's why I'll tell you. This one is from the left. This one we can get the x, y direction. We can get the value will be here. This one, you see somewhere between. So of course, based on this one K 0.5, 0.7. Because it's 0.677, I just say 0.7 for you to know. Then you can get the values. Area give you X, I will give to you. So now of course PCR X, PCR Y for different situation. The K will be work out. That means we can work out some values. So then we can use find a PCR Y is less than PCR X, less than this one. And of course we can get these values. Okay? Because otherwise, if this one greater than this one already failed because of buckling. So the one for PCR of these values should be go to this lowest value. So then, of course, this value is less than the yield strength, and the buckling will happen of these things. Okay? So, of course, this one just give you an idea a little bit. Of course, in the exam question, so the situation will much more simple. So let you know if you understand lecture example 3, you should be fine to understand. Okay? But of course, tutorial question will show you how you can understand this thing. So of course, this is why you need the knowledge to solve this problem. Okay, that's all for this part.